So we are happy to have Wenyuan from USC who will tell us about Lagrangian Correspondence, Microlocal Sheaves.
Okay, thank you very much for the invitation. It's my pleasure to be here. So the talk today would be about Lagrangian correspondences and microlocal sheaves. This is joint work in preparation with David Nadler and Vivek Shende. The hope is that this paper would come at some point in the near future, maybe by the end of this year. All right, so I'll start by explaining the two keywords appearing in the title. What is Lagrangian correspondence and what is microlocal sheaves and what I'm going to do with them. So there is kind of a, as you might know, a well-known saying by Weinstein that everything is Lagrangian. Of course, what he means is that presumably everything in symplectic geometry is Lagrangian. Well, rather than being just a slogan, this the sentence has a slightly more precise meaning, which is to say that Lagrangians should be used to understand, how to say, relations between different symplectic manifolds. And this would be what's called Lagrangian correspondences. And roughly, Lagrangian correspondences are just some generalizations of maps, well, reasonable maps between symplectic manifolds. The definition is as follows. Let's say x1 omega 1 and x2 omega 2 are symplectic manifolds. Then a Lagrangian correspondence is simply a Lagrangian submanifold inside the product. I'm going to take the product of x1 times x2, and I'll take the symplectic form given by negative omega 1, direct sum omega 2, and pulling back negative omega 1 and pulling back omega 2. And this would give me a symplectic form on the product. Of course, there's reason to add a negative sign here. So let's look at the simplest example and you'll see why there is such a negative sign. I said that we want to look at maps between symplectic manifold. What is the most typical map between symplectic manifold? Let's look at open symplectic embedding, where being symplectic means that pullback of omega 2 is equal to omega 1. And in this case, well, what is the thing in the product that should characterize this map? Well, it would be the graph of this map. I can take the graph consisting of x1 and phi x1, where x1 lives inside my domain. And if you plug into the product symplectic form given by negative omega 1 plus omega 2, you'll see that this graph is now a Lagrangian submanifold. Or in our case, it is a Lagrangian correspondence. So yeah, the negative sign here is exactly used to ensure that when you take the graph of symplectomorphism, or more generally in symplectic embedding, you get the graph you get is a Lagrangian correspondence. And from now on, I'll use some abbreviation where I would denote this product symplectic manifold as x1 minus times x2, where the minus sign means that I'm shifting the symplectic form. Okay. Of course, there are supposed to be, I guess, more examples rather than just symplectomorphisms. Let me try to give some other examples. Oh, okay. So first write down the simple example here. Well, what happens if you take one of x1 or x2 to be a point? So let's say if one of the manifold is a point, well, and a Lagrangian correspondence between a point and a symplectic manifold X is just a single Lagrangian submanifold inside X. This is a Lagrangian correspondence. So you also see that it just generalizes the concept of an arbitrary Lagrangian submanifold inside a symplectic. Okay, let's try to give more examples. Well, say this is another example. I have a moment map from my symplectic manifold X to the some dual Lie algebra of some Lie group. Say this is the moment map. Of a Hamiltonian group action. Say a Hamiltonian G action on my symplectic manifold X, which is, okay, of course, symplectic. And now I can also just look at the graph of such G action. So what would the graph be? Let me denote it by gamma of mu. So given a Hamiltonian G action, I can look at the graph of each map given by phi G. Phi G would be a symplectomorphism on the manifold, on the symplectic manifold X. So this sits inside, of course, X cross X, or X minus cross X. But of course, we want to encode all possible G's. So what we would do is to take, okay, also G together with, I think, if I remember the formula correctly, negative of the moment map times, well, applied to the point phi G of X. All right. And now, so this thing lives in X minus cross X cross G cross the dual Lie algebra. And in fact, you might notice that G times its dual Lie algebra has a symplectic form. Indeed, it is symplectomorphic to just the cotangent bundle of G. Well, all the examples up to now we gave seems to be more or less generalizations of maps or symplectomorphisms or symplectomorphisms between them, or in this special case, just single Lagrangian. There are some more non-trivial examples I can give. Let me show you an example. So let's say D is a symplectic divisor inside of X. And let's consider, say, Y to be the contact boundary of the complement. Assume that the complement is a Liouville domain, has some convexity property, then we can take the complement and the boundary Y is, let's say, it's known as a contact hypersurface. And I can also write down a Lagrangian inside the product of X times the divisor. So I want to build some correspondence between X and the divisor itself. Okay, between X minus D and the divisor itself. It would be the following. It would consist of, okay, X and pi x, where let's say x lives inside x minus d, and I guess pi is the projection from the contact boundary to the divisor itself. So the contact boundary is the boundary of the neighborhood of the smooth symplectic divisor, and there is a natural projection map of the bipolar. So one can check that this, which lives inside x minus d times d, is also a Lagrangian correspondence. All right. So these examples trying to illustrate or trying to convince you that the notion of Lagrangian correspondences is a useful notion in symplectic geometry. It captures many interesting objects that we would like to study. Okay, then what do we want to do with them? So here is the hope. Like I said, that the goal of defining those Lagrangian correspondences is that we want to view them as generalized maps between symplectic manifolds. In other words, like we want to define the category of, let's say, all symplectic manifolds so that, well, for a category, we need to specify objects and morphisms. Well, objects are just themselves symplectic manifolds. And what about morphisms? Morphisms will just be Lagrangian correspondences between them. But okay, if you know more about symplectic geometry, like having now you're given a symplectic manifold, which is the product x1, x2, and you're given some Lagrangian submanifolds inside that. And now you would probably have something in mind, because for Lagrangian submanifolds, I can associate some other invariance, which is the Lagrangian Floer homology. Okay, so for two different Lagrangians, in the same, let's say x minus times x2, we can associate them with the Floer cohomology or the Floer cochains between those two Lagrangians. And usually the Floer cochains is realized as, or is viewed as, some morphisms between Lagrangians. And this is to say that the morphism space themselves, which are Lagrangian correspondences, well, for those morphism spaces, we can take morphisms of that. So in other words, I would just use the word two morphisms to say that, okay, for the morphisms between symplectic manifolds, which are Lagrangian themselves, I can take their Floer cohomology to get, I guess, a two category of all symplectic manifolds. Okay, so now let me try to say a little bit more about maybe Fukaya categories and Lagrangian correspondences.
What about compositions?
Ah, yes. So the composition would be the main topic today. So I haven't, I realize I haven't defined compositions of Lagrangian correspondences. Let me define them now. Okay. Yeah, of course, to define a category, you need to specify how to compose morphisms. So, well, let's say you have a morphism, which is a Lagrangian correspondence between x1, x2, and well, you want to compose. So now you take some other morphism, starting from x2 going to x3. This would be a correspondence inside x2 times x3. Say they're Lagrangian correspondences. How to define their composition? Okay, the convention I'm gonna follow, I hope I will be consistent throughout the talk, but I cannot ensure that I will be. I'll denote their composition by L23 goes with L12, and this would by definition be the following subset. So the composition, of course, it should be a subset inside x1 minus times x3. And I'll take following points, x1, x3, so that, well, there exists a point x2 inside the middle factor x2 where, okay, x1, x2 lives inside L12 and x2, x3 lives inside L2. Right. So this would be my definition of composition. And if you plug into the simplest example of a symplectomorphism, you'll see that this is exactly composed in symplectomorphisms because, well, if you look at the graph, x, phi x, and a point in a different graph, x and psi x, then the composition would require that the target inside x2 is the same as the point you start with inside x2. So the composition would just be the composition of their graphs. And a remark is that, okay, for generic choices of Lagrangians, the composition remains to be okay, I think in general, immersed Lagrangians up to some genericity condition that you can show image is still a smooth submanifold that is a Lagrangian, but you cannot ensure embeddedness in general. Okay. This is the geometric setting, and now we know what we want to do because we want to study, I guess, the Floer cohomology between these Lagrangian correspondences. So let's talk a little bit about Fukaya categories. And what Fukaya category is for a symplectic manifold, we assign let me write f of x for the Fukaya category of x. And the Fukaya category is a category. Okay, it is not a strictly speaking one category, but the Fukaya category, as a category, it should have objects and morphisms. So objects themselves are, okay, Lagrangians L inside the symplectic manifold X, together with some additional conditions, which will be very important in a second. And what about morphisms? So morphisms will be like Lagrangian Floer cochains, which I denote by CF, between two different Lagrangians. And the morphism is itself a space, but out of the morphism space, I can define an A-infinity relation. Namely, I would define on the morphism space the differential and compositions and further homotopies of the compositions and so on and so on. And A-infinity category, roughly speaking, is just a I guess a homotopy coherent version of a DG category in some sense. Okay. Now now I omitted some conditions here. What are the conditions? This is going to be important in a second. So first of all, not all Lagrangians define objects in the Fukaya category. And there is typically some obstruction to define an object inside the Fukaya category, and the obstruction is given by some, is controlled by some curved A-infinity algebra. And in order to make it an object, we need to equip it with some bounding cochains that solve some Morikawa equation. Whatever it is a Lagrangian together with some extra data that would in general give you an object in the Fukaya category. And the extra data would control the disk bubbling of pseudo-holomorphic curves, which would be necessary to compute morphisms in Floer cochains. Okay. And secondly, what is the morphism space? I haven't explained it at all. The morphism space, Lagrangian Floer cochains, those are vector spaces generated by the intersection points of L1 and L2 when they intersect transversely. So this is to say that we'll need to make a perturbation to the Lagrangian submanifold, and when they're intersecting transversely, I can generate this vector space of, well, freely spanned by all its intersection points. And this is to say that computing Floer homology requires genericity assumption. All right. The generators of the morphisms, as I said, are intersection points between Lagrangian submanifold and the, I said to define actually composition and differential, I'll need to count through the holomorphic curves in the chain complex whose endpoints are on the Lagrangian and, whose boundary condition are specified the Lagrangian and have endpoints on those intersection points, where a rough picture of differential would be a pseudo-holomorphic curve that has this kind of boundary conditions where composition would be more complicated since you need 2 input and 1 output. So you have an intersection point of L0, L1 and an intersection point L1, L2. Their composition would be a point inside L0 intersect L2 where you can find such a holomorphic triangle. And you can imagine there are further higher compositions and so on. But all right, so now let's go back to our original proposal. We can form we want to study Lagrangian Floer theory inside the product symplectic morphism as the 2 morphism inside the 2 category we want to construct. So there is something nice about the Fukaya category, namely the Fukaya category of, or for the Lagrangian living inside x1 minus times x2. In other words, for a Lagrangian correspondence, let's say with bounding cochains, defines an object inside the Fukaya category of x1 minus times x2. And indeed, under some suitable assumptions, let's suppose that this is actually the Fukaya category of x1 minus tensor with the Fukaya category of x2. Under some suitable assumptions, if this holds, then it can be viewed, a Lagrangian on the left-hand side can be viewed as a let me write, okay, let me write it like this, as a bimodule of, okay, Fukaya category of x1 and Fukaya category of x2 via the Uneda embedding. What this is trying to say is that, okay, I have a Lagrangian inside product. To define a bimodule, this is to say, given any input inside x1, given any object inside x1 and any object inside x2, I can plug them in and output a vector space. And the way I output the vector space is, of course, just by taking harm with my original L12. Okay. And the fact we know is that, all right, the Lagrangians give bimodules of categories. But studying bimodules between categories, this is a more category theory question. And indeed, okay, under suitable assumptions again. All the, let's say, PG categories form a two category. And if you haven't seen the word, the adjective infinity, just ignore it for now. All right, this is to say that we already have some existing two category out of a symplectic manifold whose objects are symplectic manifolds and morphisms are just, so the objects are, say, symplectic manifolds, or say the objects are their Fukaya categories, and the morphisms will be the bimodules between them. In other words, this is to say that we have two possible proposals of defining compositions. Namely, for bimodules between categories, we can compose bimodules. In fact, this is just a generalization of composing functors between categories. But on the other hand, we have written down a geometric composition of Lagrangian submanifolds themselves. Okay, question. Are they the same composition theory? And in Floer theory, there are a lot of work related to that. Let me try to write all their names and roughly explain what is thought. This has been a series of works by Weinheim-Woodward, Mal Weinheim-Woodward. Okay. Lakili, Yansky. Fukaya, and works that are still ongoing by Botman and Wang. The short summary of all these series of results is that geometric compositions of Lagrangian submanifolds with bounding cochains. Induces algebraic compositions of bimodules or of functors. And I think it's hard to give a precise summary of what these people have done, but I think first the work of in the first works of like Weinheim, Woodward, Mao, Weinheim, Woodward, Lakili, Lubyansky, what they claim is that for some monotone closed symplectic manifolds and monotone Lagrangian submanifolds, where you automatically know the existence of bounding cochains, well, you can do compositions assuming, first of all, genericity condition and the condition that the composition is still, instead of immersed, embedded. So there are certain assumptions. First of all, like genericity, and secondly, embeddedness of the composition. And third, monotonicity. Which is to ensure that you don't need to worry about bounding cochains. All right. This appears in the first series of works, and then later people have been more ambitious. In particular, Fukaya claimed to prove that like still under genericity condition where the composition is a Lagrangian, but potentially immersed Lagrangian, so we don't have embeddedness, and assume that, and let's drop the condition of monotonicity, meaning that we don't assume, we only assume existence of bounding cochains. But they don't come up in an automatic way under the monotone case. So in these cases, you can still define compositions. And moreover, like the still ongoing work of Bachmann and Weinheim is to, first of all, trying to directly construct a virtual fundamental cycle on the corresponding moduli space. And second, also fully build up a theory of A infinity 2 category, which is not, which is, I guess, more complicated than, I guess, 2 categories, DT categories. So remark they need to assume, like, what the ongoing work of is the piece of A infinity 2 category. Right. And this framework should tell you that you can further compose again and again in a homotopically coherent way. All right. So now I've spent more than half of my time and I haven't talked about the second word in my title, and I should probably talk about that. So, Microlocal Sheaves. Or just topological Fukaya categories. So the first result in this direction is by, I guess, Nadler and Zaslow, who realized that there is some relation between sheaves on manifolds and Fukaya categories in the cotangent bundle. So more precisely, if you consider some constructible sheaves on N, this corresponds to what is known as, I guess, a version they define called the infinitesimal Fukaya category of the cotangent bundle. So let me explain the words. This is the category of constructible sheaves on a smooth manifold. The word constructible is just trying to say that, well, the sheaf or the sheaves are locally constant with respect to some, reasonable stratification of the manifold. In other words, it's a way to try to glue local systems on different strata together to get a more, complicated version of local system with respect to some given stratification. And this is typically known as the infinitesimal Fukaya category of star N. So let me explain through an example of how this correspondence happens. Let's look at the simplest cotangent bundle, maybe T star of S1. Say this is my S1 direction. There is a way to, we can write down many Lagrangian submanifolds inside T star S1, and let's consider in particular this type of Lagrangian submanifolds. All right, how do I associate it with a sheaf? In terms of pictures, what happens is that inside the cotangent bundle, you have the Liouville flow, which contracts every fiber. And what to do is to follow the inverse, this is the inverse Liouville flow or the Liouville flow, one of them. You follow the Liouville flow to contract everything to, this is called the core, which is the zero section in this case, and the limit set of the Lagrangian I started with would become a subset that is invariant under the Liouville flow. You see it, basically everything is contracted to the zero section except for the cotangent fibers, except for the part which is already cylindrical at infinity, which are preserved under the Liouville flow. And this data would tell you how you would come up with a stratification on the base S1 and how to define a sheaf. In this simple case, you will just put, you will just let the stalk of the sheaf to be K in the interior, where it hits the limit of the Lagrangian and zero elsewhere. Of course, this is mostly a heuristic picture and it's harder to explain what happens in general, but this is basically trying to explain that, well, given the Lagrangian, you can associate with some sort of sheaf type object inside the core of the manifold. And there's now a more precise statement that I can write down. In the theorem of Kunneth and Shende, they showed the following that, well, first of all, in cotangent bundles, if you specify a singular support which is a subset inside the cosphere bundle of the manifold that is isotropic or Lagrangian, then this category of constructible sheaves induced by this data of lambda, this is equivalent to the version of the Fukaya category on the cotangent bundle with some data also specified by this lambda. And of course, we need to take modules on the right-hand side because the left-hand side is, let me say, the unbounded, okay, DG, or the unbounded DG derived category of sheaves. And on the right-hand side, this is the, I added the letter W, and this means we're taking the wrapped Fukaya category of E star n. The word wrapping is trying to indicate that, well, the Lagrangians we are allowed are no longer compact, so we need to do some Hamiltonian perturbation near infinity. And the data lambda is trying to say that the Hamiltonian perturbation, the Hamiltonian isotropy, does not pass through the subset length. In other words, your Hamiltonian at infinity is controlled by some boundary conditions specified by this length. Of course, I didn't explain what either side means, and I'll not explain it. I'll write down a further generalization, which again, I'll not explain the terminology. So
the unbounded here means unbounded in both directions.
Unbounded in both directions, yes. I think it is the, like, or instead of DG, you can think of it as the derived infinity category of sheaves. Yes. And they have a more general version, which not only works for cotangent bundles, there are many other symplectic manifolds that we're interested in. So it would work for a Weinstein manifold. And the word Weinstein is trying to indicate that symplectic manifold here is exact, meaning omega is differential for one form, and also it's convex. It has convex boundary. And third, the condition is that it should deformation retract to a half-dimensional Lagrangian cellular complex. This is called the core of the Weinstein manifold. So as an example, any smooth affine variety is a Weinstein manifold, and any Stein manifold is a Weinstein manifold up to deformation. So we'll denote this as the core of my Weinstein manifold X. And instead of looking at sheaves, I'll need to look at some version called, let me say, microlocal sheaves on the core of X. And this is equivalent to the modules over the, again, wrapped Fukaya category of the Weinstein manifolds. So this theory is just to say that, okay, other than the Fukaya category, now we have indeed a more topological model of Fukaya categories on the left-hand side, defined using, okay, sheaves on manifolds. And what is this? This will be, in one word, something that comes out of some localization of sheaves on manifolds and followed by some more complicated procedure I will not explain. Okay, now I should say what we want to do. The goal now is to do Lagrangian correspondence, work on Lagrangian correspondence in the setting of microlocal sheaves instead of Fukaya categories. Let me write down morally what our main theorem says. Oh, I think I'm not at the stage of writing down the main theorem yet. Let me say, let me write down this theorem first. Well, first of all, to define the theory of Lagrangian correspondence, I should have a way to explain, to say what it means to have a Lagrangian as an object. Although under this equivalence of Fukaya categories, I know that objects in this whatever mu sheaf category will be Lagrangian submanifolds. However, I don't know an explicit way to identify them without passing through the equivalence. And there will be a reason, as we'll see, that we do not want to directly pass through the equivalence to Fukaya categories. So here is the result. Let's say L inside X is an exact embedded Lagrangian with cylindrical ends. Okay, I guess compact instead of cylindrical ends. Then they show that there is a fully faithful functor from local systems on L to this mysterious category called microlocal sheaves on the core of my manifold X. If L has massless data, namely over Z, if your Lagrangian is massless 0 and is relatively spin, you should be able to define an object in the Fukaya category. And similarly, this result is saying that for Lagrangians that have massless data, if it is exact and embedded, then you can define a Lagrangian with a local system as an object in this microlocal sheaf category. And moreover, the full faithfulness is saying that if you take the endomorphism of the local system, you get an endomorphism inside the microlocal sheaf category, which just says that Hom of a single object is equal to the homology of that object. Sorry, cohomology. Okay. Now, we don't always want to work with embedded exact Lagrangian, as we said over there, because compositions of embedded Lagrangians are not necessarily embedded Lagrangians. So there is a way to define, exact Lagrangians with, let me use a different word in the sheaf theory context. This will be called a sheaf quantization as an analog to bounding cochains. On my Lagrangian. Now, in Floer theory. Okay, so I have now, I didn't introduce what it is, but let me do it maybe later. But now I have the corresponding concepts of bounding cochains, which tells me when an immersed exact Lagrangian defines an object in the microlocal sheaf category, just as when they define objects in the Fukaya category. So now I can ask the question again, namely, is the geometric composition of Lagrangian submanifolds, maybe together with sheaf quantizations or together with sheaf theory bounding cochains, the same as the algebraic composition of bimodules? And this will be the main theorem of the talk. The short answer is yes. Geometric Okay, yes, under a suitable assumption that is necessary, which I'll explain in a second, geometric compositions of Lagrangians of exact Lagrangians with sheaf quantizations agree with algebraic compositions of bimodules for wrapped Fukaya categories. Now, if you recall, when we were saying some words about wrapped Fukaya category, we said that we need to choose some Hamiltonian perturbation near infinity. So now the natural question that now comes up is, does the Hamiltonian perturbation, or in other words, does the wrapping, or is the wrapping compatible with the composition? The answer is, in general, no, but there are some simple conditions that ensure it is the case. A simple condition is that if I look at core of x1, x2, and together with the cylindrical end of my Lagrangian L1, 2, this is a singular Lagrangian. I can compose it with the core of x1, and I ask that to be contained inside x2. In other words, the composition of the core together with the cylindrical end is contained in the core. And if this condition is satisfied, then that geometric composition is indeed the same as the algebraic composition. And of course, I should write down that in Floer theory, or in wrapped Floer theory, Lagrangian composition is also studied by Gao, and his main result says that if your exact immersed Lagrangian has bounding cochains and suppose that the projection of the Lagrangian to the target is a proper map, then L defines a functor from wrapped Fukaya category of x1 to some slight enlargement of wrapped Fukaya category of x2. And the way it maps things is that it sends a Lagrangian in the domain to the geometric composition together with bounding cochains. So this notation B means bounding cochains. And in other words, he comes up with the natural composition of bounding cochains and works out the composition when you're looking at a single functor, but without looking at compositions. Of course, it's natural to imagine that his same technique would work for compositions as well. But the reason I want to mention this result, other than the previous one, is that you notice this also has an assumption on the geometry of the Lagrangian itself. So this assumption on the projection is indeed analogous to our assumption that composition with the cylindrical end does not give you anything extra in the cylindrical end. Indeed, like a remark is that these two are related in the sense that one implies two, but we will need to replace the projection to the second factor by the projection to the first factor. due to the reason of taking some adjoint functors or switching the domain and the target. All right. This is a 1 hour talk, so I can continue a little bit. All right, let's go back to this a little bit. I said that there is a way to define something called sheaf quantization, which are analogous to bounding cochains, but I didn't say what they are in particular. I didn't write down any single formula and give you a sense on what is the thing I'm trying to prove. So in the last 5 minutes, let me try to give you some formula of what I'm trying to do. Well, what does it mean to give a sheaf quantization? What we want to do is, okay, start typically for an exactly embedded Lagrangian, start with the Lagrangian. I can equip it with an object in this microlocal sheaf category as a topological model of the packet. But when the Lagrangian is immersed, I cannot always do that. So I'll first try to lift my local system to something which I call sheaf quantization. And then this sheaf quantization would naturally give me an object over here. So let me try to write down what is the sheaf quantization. The sheaf quantization lives inside the core of x times t star of r together with a boundary condition specified by L. So what does this mean? Here, L lives inside the boundary of x times t star of r as a Lagrangian submanifold. Okay, and this the choice of an object in the middle is what I call the sheaf quantization of F. The reason to call it sheaf quantization is basically because if you think about, for example, other types of fluid theory or Lagrangian contact homology, assigning an object in this category with respect to the boundary condition being the Lagrangian lift is the same as assigning a one-dimensional representation to this algebra, and assigning it with one-dimensional representation is, in the world of Lagrangian contact homology, the same as assigning a bounding cochain to the corresponding Fukaya A-infinity algebra. All right, given this formula, I can finally write down what is the final diagram that I'm able to produce. So the final diagram would be the following. On the left-hand side, I have just the topological data of local systems on my Lagrangians. I can just compose the data of local systems by doing some composition. And I have my refinement of the data, which I call sheaf quantization, or if you like, bounding cochains, on its lifting as a Lagrangian. And I can do compositions there. And finally, I have my mu sheaf category on the product. And I can compose the mu sheaves on their product. The point is that this is an algebraic composition that follows formally by the fact that these mu sheaf categories are presentable and dualizable in an appropriate sense. Under some suitable categorical assumptions, this naturally is defined. And on the left-hand side, this is purely topological. What I'm doing is just pulling back the local system onto the product and restricting it to the diagonal. And the main theorem says that the whole diagram commutes and further commutes up to taking all the other higher compositions, which means that I'm lifting the topological data to some geometric data, which I call sheaf quantization. And then by restriction to the algebraic side, I can get the composition of functors I want. I really used the whole hour, so I should stop here and thank you very much.
So you mentioned the sheaf quantization. So for embedded Lagrangian,
Yes.
the brain data.
Yes, for an embedded Lagrangian, okay, assume there exists brain data, then this map will be an equivalence. And this would be fully faithful. So the thing I didn't say is that, okay, for embedded Lagrangians, the left functor is an equivalence and the right functor is fully faithful. And this realizes the functor for embedded Lagrangians I wrote over there.
And so in your setting, there are no curved algebras. Everything comes with uncurved.
Yeah, everything comes with everything is uncurved in this setting. However, like there is in principle a theory that you can there is a theory that would help you to try to characterize whether there is a way to get a sheaf quantization using some version of curved A infinity algebra in some recent work by Yuichi Ike and Tatsuki Kuwagaki. Although, and I think that theory is compatible with this particular setting. However, the computation of that curved A infinity algebra, or to find a bounding cochain using that curved A infinity algebra seems pretty delicate.
Can you maybe show on this example, like on the T star S1 example?
Yes.
Like show all the objects.
Yes. So in the T star, so in cotangent bundles, I can write down some explicit examples of what our main theorem means. So like on T star S1, so let's say on T star M, I have a Lagrangian sitting inside my T star M. What I will need to do is to lift it to, well, this is a Lagrangian, and I'm lifting it to, let's say, the contact boundary of my T star M times R. And this is what I call my Lagrangian lift. It will be determined by the exactness structure. So the diagram I have over there means that on one side, I have local systems of L, and the sheaf quantization data is sheaves. Well, now it's sheaves on M times R. And having a Lagrangian is equivalent to saying I have a conic Lagrangian, so I can put this as a singular support condition. And now I can restrict to get an object in the Fukaya category of T star of M, and the wrapped Fukaya category of T star M is local systems on M. So what I will do here is I'll restrict at R equals infinity. And what I'm doing here is I would, okay, this is a little bit harder to explain, but I'll need to microlocally restrict my sheaf by taking the microstalk. And this is the diagram of like sheaves I have, by which I mean a sheaf quantization. And typically, the local systems on L should really be a twisted version of local system whose twisting is governed by the mass of data or by the Gauss map composed with the J homomorphism. But when such obstruction trivial, we can fix an identification, and this would be the diagram we see. And the composition theory we'll need to show is that the composition theory for sheaves on M times R and composition theory for sheaves on M versus this more mysterious composition living inside the cotangent bundle agrees. So in particular, one of the main content in the diagram inside the main theorem is we'll need to define these functors. Okay, we'll need to define this functor in general, although this functor in the sheaf setting, it is defined because for sheaves you can compose them. But for this microsheaves, for this mu sheaf category, the composition is not defined, and we'll need to write down a definition of composition by hand and show that they're associative.
So is part of this statement also showing that the composition has a quantization?
Yeah, so in particular, this is to say that if you take compositions of Lagrangians, if what you started with have sheaf quantizations, then the composition also have quantizations. And moreover, it doesn't matter. You might recall I've mentioned some genericity conditions. So this theory over here, most of this theory does not depend on any genericity condition, meaning that as long as I have L12 and L23, I can compose no matter what the target looks like. It doesn't need to be embedded, it doesn't need to be immersed, and doesn't need to be smooth. And the only thing where we use smoothness is when I write down that the target is local systems on L13. But if the composition, if the set theoretic composition is some very singular thing, I can still write down a corresponding category and show the commutative diagram like this. And indeed, this is the main reason that we would like to work with, but I guess one of the main reasons we would like to work with sheaf theory, which is that we don't need to incorporate all the genericity condition, which makes showing higher coherence super hard. And I guess another reason to do things in sheaf theory is that, well, the theory of, I guess, stable infinity categories is better developed than the theory of A infinity 2 categories at the moment, perhaps.
Do you not need to use infinity 2 categories instead of stable infinities?
That's true. We'll need to use some infinity 2 categories, of course. Yeah, but at least the infinity 2 category structure on this side is well, almost follows for free, because you have that, okay, I guess presentable stable infinity categories form an infinity 2 category.
More questions? Okay, if not, let's thank the speaker.